Why is Helmholtz free energy key to the second law? Have you ever wondered why some processes happen naturally while others seem to requiring a push? The answer lies in the concept of Helmholtz free energy and its connection to the second law of thermodynamics. Let's break this down in a way that makes sense. The second law of thermodynamics tells us that in an isolated system, entropy, which is a measure of disorder, tends to increase over time. But what if the system can exchange heat with its surroundings while keeping its temperature and volume constant? In these cases, just looking at entropy doesn't give us the full picture of whether a process will occur spontaneously. This is where Helmholtz free energy comes into play. It is a useful tool for predicting spontaneity in systems at constant temperature and volume. The formula for Helmholtz free energy is simple. It is the internal energy of the system minus the product of absolute temperature and entropy. In this equation, the internal energy represents the total energy stored within the system. Absolute temperature is measured in Kelvin, and entropy reflects the level of disorder. The term involving temperature and entropy shows us how much energy is not available to do useful work because it is tied up in disorder. For a process to occur spontaneously at constant temperature and volume, the Helmholtz free energy must either decrease or remain the same. When the system reaches equilibrium, the Helmholtz free energy is at its lowest possible value. At this point, the system cannot perform any more useful work without changing its temperature or volume. In practical terms, Helmholtz free energy indicates the maximum work that can be extracted from a system under these specific conditions. If the free energy decreases during a process, it means that the process can happen spontaneously and do useful work. Conversely, if the free energy increases, the process is non-spontaneous in that environment. This concept is particularly relevant in fields like physics and chemistry, especially when examining systems where volume remains constant but temperature is steady. For example, certain chemical reactions or physical processes in closed containers fit this scenario perfectly. Unlike Gibbs free energy, which is often used in chemistry for constant pressure and temperature situations, Helmholtz free energy is tailored for constant volume cases. This makes it a vital concept for understanding how energy, disorder, and the ability to perform work interact in various systems. In essence, Helmholtz free energy is key to the second law because it translates the abstract notion of increasing entropy into a clear criterion for spontaneity and work potential in systems at constant temperature and volume. This understanding makes the principles of thermodynamics more relatable and applicable to real-world scenarios.